However, the following results say that if the convergence is uniform, then the limit function is also continuous. Okay, so if a sequence of continuous functions converging to a point, then it is not necessarily that the limit point is also continuous function. But if a sequence Fn of continuous functions converges to a function f uniformly, then f must be continuous. Okay, so this we will prove in the next theorem, which says that let x and y be metric spaces, Fn be a sequence of continuous functions, each defined on x to y, and f is a function from x to y. If Fn converges to f uniformly on x, then f is continuous on x. In other words, a uniform limit of a sequence of continuous functions is continuous. Let us prove this. Very simple proof, not very difficult. Let epsilon greater than 0 be given and x naught in x be arbitrary. So, we have taken x naught arbitrary and epsilon greater than 0. Since Fn converges to f uniformly, by the definition, there exists a positive integer n depending on epsilon only, such that for all x in x, d Fn x fx is less than epsilon by 3 for all n is greater than n. So, this is by the definition of the uniform convergence. Now, let n naught is greater than capital N, since Fn naught is continuous at x naught. Okay, because Fn naught is continuous because this is a sequence of continuous functions. So, in particular, Fn naught is also continuous. So, it is continuous at a particular point x naught. We can choose delta is greater than 0 such that for all x, okay, in the open ball with center x naught and radius lambda, that is to say dx x naught is less than delta, we have d y f n naught x Fn naught x naught is less than epsilon by 3. So, this is because of the continuity of the function f n naught. Now, by using previous two, this one and this one, what we can do here is we can have for all x in the open ball with center at x naught and radius delta, we have dfx fx naught is less than or equal to. So, here we have added this term, here you have this term and then this one extra. So, here this is less than epsilon by 2, this is less than epsilon by 3, this is less than epsilon by 3, this is, so this is the whole, this is equal to epsilon, so this is less than epsilon, and therefore, f is continuous at x naught. So, this way we can prove that the function f is continuous. So, it means that if Fn is a sequence of continuous functions converges uniformly to f, then the function f is also continuous. So, we have proved that, but it is not true in case when the convergence is pointwise. Okay. Now, we have a proposition which says that if x and y be metric spaces and Fn be a sequence of functions from x to y, then for any function f from x to y, Fn converges uniformly to f if and only if Fn converges uniformly to f if and only if the supremum of this, yani the supremum over x in x, d Fn x fx, this supremum of this converges to 0 as n tends to infinity. So, this is also a very nice result which provides the criteria of uniform convergence, that is to say, which provides the necessary and sufficient condition for a uniform convergent of a sequence of functions. So, assume that Fn converges uniformly to F. Then, by the definition, for every epsilon positive, there exists a positive integer n depending only on epsilon, such that this inequality holds for all natural number n greater than n and all x is n. Therefore, now you take this is less than epsilon. It means that we can take and for all x. So we can take the supremum over here for all x is in x. So this is also less than epsilon, less than or equal to epsilon for all n is equal to 0. Okay, because here is we are taking the supremum, so supremum can be equal to epsilon. And since epsilon was arbitrary, so we can say that this converges to 0 as n tends to infinity. So this term converges to 0 as n tends to infinity. For the converse, assume that this converges to 0 as n tends to infinity. Then again, by the definition of the convergence, for a given epsilon positive, there exists a positive integer n depending only on epsilon, such that this is less than epsilon for all n is greater than 0. But this means what? This is your, so supremum of this is less than epsilon. It means that this term must be less than epsilon for all n and for all x. So this is, it means that Fn converges uniformly to F. Now, we have a remark. We say that the above proposition says that the uniform convergence means that the maximal distance between Fn and F goes to 0. So here is, you see, if Fn converges uniformly to F, then that maximum distance between Fn and F converges to 0. Okay. So here is the remark say, the proposition says that the uniform convergence means the maximal distance between Fn and F goes to 0. Now we have a example. Let us take x is equal to close interval 0, 1 and y is equal to r with the usual metric, and Fn be a sequence of functions defined as Fnx is equal to 2nx when x lies between 0 and 1 over 2n, and Fnx is equal to minus 2nx plus 2 when x lies between 1 over 2n and 1 over n, and Fnx is equal to 0 when x lies between 1 over n and 1. And let Fx is equal to 0 for x in R. Okay, then we see that Fn converges to F pointwise on the closed interval 0, 1, because at every point x in the closed interval 0, 1, the value of the function, okay, Fn x eventually becomes 0 as n tends to infinity. So for x is equal to 0, the value is always 0. Okay, so because for x is equal to 0, this is 0. Okay, so this is equal to 0. Okay, so and for x is greater than 0, so x is greater, the tent will eventually pass to the left of x. So here is this is the graph of the function. Okay, so you start from x is equal to 0, it is 0, and then from x to 1 over x. So x to 1 over x, it goes up to 1 and then come down, and then for the rest when x it is equal to 0. So hence Fn does not converge uniformly to F on x is equal to 0, but f of x is equal to 0. So f of x is equal to 0 is this one. So it does not converge uniformly. See, it is going up, then coming down, and then it is same. So only here is converging, but not on this portion. So as the maximum value of Fn is 1. That is, the supremum of this is equal to 1 for all n. So it is not the minimum value, because in the previous result says that the supremum of this distance converges to 0. But here you can see that the supremum of this converges, it is equal to 1, which does not, it means that the supremum of this does not converge to 0. Okay. Now we have the Cauchy criteria, as we have discussed. You have discussed the Cauchy criteria in the real analysis case. So Cauchy criteria says that if you have a sequence, so let us, or you can let us take Fn be a sequence of functions defined on a metric space X to a complete metric space Y. Okay, so here is Fn is a sequence of functions defined from a metric space X to a complete metric space Y. Then there exists a continuous function f from X to Y such that Fn converges to f uniformly if and only if the following conditions holds good. What is the condition? Condition that for every epsilon positive there exists a positive integer n such that d fmx fnx is less than epsilon for all mn is greater than in capital N and all x is in n. And this means what? This means that f n x, this is a Cauchy sequence of real numbers. F m x, if it is true for all x, keep in mind it is true for all x, so this is a Cauchy sequence of real numbers. Cauchy sequence, this is a Cauchy sequence of sequence of elements of Y. So here is we are taking Y is your complete metric space. So Fn converges to F uniformly, okay, then this condition holds good, or if this condition holds good, then Fn converges to F uniformly. So this is known as the Cauchy criteria. Suppose that Fn converges to F uniformly on X, then by the definition for any given epsilon positive there exists a positive integer n such that d fn x fx is less than epsilon y2 for all n is greater than n and all x in x. Thus, for all mn greater than n or all x, f mx fn x dy fmx fnx is less than epsilon by 2, and here we can take instead of m is n d fnx fx is less than epsilon by 2. So for all mn is greater than n and l is greater than or equal to d fmx fnx is less than or equal to this term plus this term. Okay, so this is less than or equal to this should be less than or equal to this one plus this one, but this is less than epsilon by 2, this is less than epsilon by 2, the whole thing is less than epsilon, and so this condition holds good. Okay, now to prove the converse part, assume that this condition holds good for all mn is greater than capital N and x is in x. Okay, then we have to prove that Fn converges to F uniformly. So for each x is in x, the sequence Fnx is a Cauchy sequence in a complete metric space Y. Okay, Fnx, from here as I mentioned that from the definition this is a Cauchy sequence because it is true for all x. If it is true for some x, then only for particular that point Fmx or Fnx is a Cauchy sequence, not for all x. So here is the important thing is that because this inequality holds good for all x is in x, therefore Fmx for all x is a Cauchy sequence of points of Y. But Y is, we are assuming that it is a complete metric space, so it will converge to some point f of x. So this they converge to some point f of x. Now we claim that Fn converges to f uniformly on x. We have to prove that Fn converges uniformly to x. So if epsilon greater than 0 is given, then we can choose n such that for all small n is greater than capital N, we have d fn x comma fn plus kx is less than epsilon by 2 for all k runs from 1, 2 and so on, and all x in x. This is why, this is because here you can choose m is equal to n and n is equal to n plus k, and then we can take k approaches to infinity. So k approaches to infinity, so this is equal to limit of this one. Okay, so because you can take the limit inside and this function is continuous dy, so you can write it like this one, but this is less than epsilon by 2, and therefore we can see that this is less than epsilon for all n is greater than n and all x is in n. Hence Fn converges to f uniformly on x. Okay, this is the proof. So now as a remark, we can say that it is known that the uniform convergence implies point-wise convergence. However, the following theorem, which is known as Dini's theorem, provides the condition under which the converse holds good. So what is the converse? Converse is the following. So it is called Dini theorem. The Dini theorem that so let XD be a compact metric space. So here is the important thing is that we have to use the compactness of the domain set. Okay, and f is a continuous function, real valued continuous function from x to r, and Fn is a sequence of continuous functions from x to r, or not only such that fn plus 1x is less than or equal to fnx. That is to say, fn is a decreasing sequence of continuous functions. Okay, decreasing sequence means that fn plus 1x is less than or equal to fnx for all n and all x is in x. Then, and if Fn converges pointwise to f, if Fn converges pointwise to f, then the convergence is uniform. So, if Fn converges pointwise to f, then this convergence is uniform. Now, here are what are the things? The thing is that number one, it is a particular case. We are not considering the function f. The function f from the metric space x to another metric space y. So, in particular, we are considering y is equal to r, number one. Number two, here is the x we are assuming is a compact metric space, not a journal complete or any other metric space. It is a compact metric space. Similarly, we are considering the sequence of functions Fn from x to a real valued function from x to, not from x to another metric, any other metric y. So it is a particular kind of metric which is equal to r. And the second thing is that the sequence of functions Fn is a decreasing sequence of continuous functions. Okay, so this is the decreasing sequence of continuous functions. Then if this sequence converges pointwise, then the convergence will be uniform. So let us prove this one. So to prove this one, we can take for each natural number define g and x is equal to fnx minus f of x. Then gn is a sequence of continuous functions on a compact space x that converges to 0. Okay, because this fnx converges to f, so this will converge to 0. So this g and x is a sequence, and Fn is a continuous function, F is continuous function, difference of continuous function is continuous. So Gn is continuous and this converges to F. So the whole thing will converge to 0. So Gnx converges to 0 pointwise. So it means that Gn, which is we have defined as Fn minus F, is a sequence. Gn is a sequence of continuous functions defined on a compact set X that converges pointwise to 0. And also for each integer, for each natural number n, Gn plus 1x is less than or equal to Gnx and it is greater than or equal to 0. So for all x. So if we show that Gn converges uniformly to 0, then we can say that Fn converges uniformly to F. So for that, let epsilon be given and consider the set On is the set of all point x such that Gnx is less than epsilon. But this is what? This is less than epsilon. So this is equal to Gn inverse open set minus infinity to epsilon. And then for each n, On is an open set, and because Gn is continuous and this set is open set, so inverse image of open set is open, so Gn is open. So for each n, Gn is an open set as it is the inverse image of open set by a continuous function. Now since Gn converges pointwise to 0, for each epsilon, for each point x in x, there exists a positive integer n such that g and x is less than 0 for all n is greater than. It must be because this is gn is greater than 0. So if you take the mod of g and x minus g converges to 0, so it's 0. So that is g and x, that is equal to g and x is less than epsilon for all n is greater than 0. And this implies that this implies that this x must be an element of g and x from the condition g and x is less than. So x belongs to Gon for all n is greater than n. Hence On, this is an open cover of x. That is the whole x can be written as a union of Ons. Okay. And now since x is compact, so there exists a finite subcover of On because x is compact. So every compact metric, every open cover has a finite subcover, okay, because x is compact. So since x is compact, this open cover has a finite subcover, okay. So then we can have there exist On1, On2. So x is equal to this one for some n1 is less than n2 and so. Okay, now since this is the decreasing sequence, from here this is holds good for all n. We can see that On is a subset of On plus 1 and so on. And so x is equal to, because all these are subset of this one, so this is a subset of this, this is a subset of this, this is a subset of this, so this all equal to Onk. Now write n is equal to nk. Then g and x is less than epsilon for all x is in x. As g and x is decreasing, we have g and x minus 0 is equal to g and x is less than or equal to g capital Nx is less than epsilon for all n is n and all x is n. It means what? It means that g and x converges uniformly to 0, and therefore we have proved that Gn converges uniformly, then Fn converges uniformly to F. So that is the proof of the Dini theorem. Now, the following example shows that the hypothesis of the Dini theorem, where we are considering X is compact, Fn are continuous and F is continuous, are each necessary in the above theorem. So it means that in the above theorem, if X is not continuous, the above theorem or the Dini theorem does not hold good. And also if Fn are not continuous, even then the Dini theorem will not hold good, and if f is not continuous, even then the Dini theorem will not hold good. So these assumptions are very important in the Dini's theorem. So we will see this in the following 3 examples. So first example, let us consider a metric space X which is equal to open interval 0, 1 with the usual metric. Okay. So what we have taken, see here is the X is not compact. So of course this is not compact, and Fn is a sequence of continuous functions on X defined as Fn x is equal to x raised to the power n. So this is continuous function. Then it is well known that X is not compact, and Fn decreases pointwise to 0, and hence in view of the proposition the convergence is not uniform, as the supremum of this is equal to 1. Because if it is the convergence is uniform, then the supremum of this, okay, will approach to 0, but here the supremum of this is equal to 1, so the convergence is not uniform. Okay. So you see that if the space is not the compact space, then the convergence is not uniform. The second example, consider the sequence Fn defined by x upon n in x upon mod of x upon n. Then Fn is a sequence of continuous functions and monotonically converges to 0, but the convergence is not uniform. So we can have this kind of sequence or this kind of the sequence. Okay. Now take another example. In the next example, we are considering that Fn is a sequence of functions defined in this way, that Fn x is equal to x square if x is less than 1 and it is equal to 0 else. Then Fn is monotonically decreasing pointwise to 0, and the domain is compact, but the convergence is not uniform. The third one is example we are considering a sequence Fn defined as Fn x is equal to nx upon 1 plus n square x square. Okay, then Fn is continuous and goes to 0 pointwise, but not monotonically. And if we take x is equal to the closed interval 0, 1, then the domain is compact, yet the convergence is not uniform, since Fn 1 over n is equal to 1 over 2 for all n. Okay, so that is the main thing, and then we have several exercises. Okay, so here are several exercises, and these exercises you can do by yourself. So let us take the first exercise. I have given already the proof. We say that if x and y are metric spaces, Fn be a sequence of continuous functions is defined on a metric space x to a metric space y, and f is a function from x to y. If Fn converges uniformly to f and xn is a sequence in x that converges to x, then show that Fn xn converges to f of x. Okay, so what is this? So first is that Fn is a sequence of continuous functions that converges uniformly to f, and xn converges to x, then f and xn converges to f of x. And show also by an example that this is not true in the case of pointwise convergence of f of n. So here is if this is pointwise convergence, then this statement does not hold good. Now let us take the proof, the simple proof. So we can take an epsilon is greater than 0, then there exists a positive integer n1 such that this is holds good. Now, since Fn converges to F uniformly, okay, then the F must be a continuous function by theorem this one. And since Xn converges to X, so we have Fn converges to F of X. And therefore, there exists a positive integer n such that this is holds good. And now, for all n is greater than maximum of n1, n2, we can write this is less than or equal to this plus this one by triangle inequality, but this is less than epsilon. So, this is less than epsilon, and it means that the Fn xn converges to F of xn. Now, here is we have, keep in mind, here is Fn was a sequence of continuous functions. So, let us take here is x and y are real numbers with usual matrix, and Fn be a sequence defined in this way, Fn x is equal to this one and f of x is equal to 0. Then show that Fn converges pointwise to f but not uniformly to f. Now, here is again the proof is here is it is given. So, you can see this proof, but I would like to mention that because this function, this is not a sequence of continuous functions. Okay, this functions, the sequence is not. So, here is you can see that uniform converges pointwise, sorry, this converges pointwise but not uniformly to f. So, what would be the graph? Graph of the function is not continuous. So, here is the graph is this one, it is coming here is this, and then we have a jump over here and then is going up, and then we have a jump here and then coming down and then straight is this one. So, here is this is the point 1 over n 0. So, and here is the point is 0 1. So, we have this function is we have a discontinuity at this point and this point, but here is we have taken that the Fn is a sequence of continuous functions, and then this sequence of functions converges uniformly but not converges pointwise but not uniformly, and that you can prove. Here is I have given the proof and you can see very easily, and there are several others exercises. So, there are different exercises that you can see by yourself, very simple one, and here is one more exercise. Prove that the sequence Fn defined by this is uniformly convergent on it but not uniformly convergent on this one. So, here is you see this is the closed interval alpha infinity, alpha must be greater than 0. So, on this one, this space is uniformly convergent, but not on this space it is uniformly convergent. So, I have given the proof that you can see. And then again I have another exercise which says that the sequence Fn defined by 1 over 1 plus xn, then find the limit of the sequence. Okay. The other thing is that when Fn converges uniformly to f on the closed interval 0a, where a lies between 0 and 1, and show that Fn does not converge uniformly to f on the closed interval 0, 1. So, this is also given. So, proof is given, you can see by yourself. Okay. So, here is again you have several exercises, and their proofs are also given. Here is this is also a exercise with proof. Okay. Here is again this is these are several exercises with proof. Show that the sequence Fn defined by this does not converge uniformly on this one. Okay. And there are several other exercises without proof that you can see. Here is again we have another exercise, and this is with the proof, and this exercise, these two exercises are without proof. Okay. So, I stop over here. Okay, and I hope that you can solve these exercises by yourself. If you will find any difficulty, first you try to solve by yourself. If you find any difficulty, then see the proof. Okay, the proof of the others okay, where I have not given the proof. For example, the proof you can see here is I have not given the proof, but the proof of this must be very similar to the proof of the other exercises where the proof is already given, and that's why I left. And you try to your best to solve the exercises which are given without proof, like all these exercises are given without proof and whose proof are very similar to the proof of these exercises. So I hope that you can do it by yourself, and if you find any difficulty, and then you can first you, if you can find any difficulty to prove these exercises, only then you see the given proof. Otherwise don't see the given proof. First you try without looking the proof given in these talks. So thank you very much.